Now, last time we saw the full form of the conservation momentum equation. It's huge, there's so much going on there, but it's not really going to be anything we ever use. We're never going to use the full form because that's meant for like CFD codes, and the full form at least is meant for very, very advanced CFD codes doing very, very difficult problems. For us though, we need to simplify it down so it's actually more easily used. So how do we do that? Well, make a few important assumptions. First off, no body force. Air is light, so gravity is negligible. Air is not charged. It's neutral, so we don't have to worry about any charges. So magnetism, electrical charge, gravity, they're not really doing anything. So we're going to say that last term, that's 0. Second, we're saying it's inviscid. So with that, we write it as if our viscosity is equal to 0, but simply because our viscous effects at these speeds are negligible. Are they negligible everywhere? No. In our boundary layer, we actually do have to account for them, but for most of the problems we do, we can just assume that we're outside the boundary layer and calculate everything based off of that. As a note, viscosity is not actually equal to 0. We're just pretending like it is because these effects are very, very small. And finally, that it's steady. So any time derivatives will go to 0. And this is true for most of our flows because most of the time there's no acceleration. We're at steady state, we're at a cruising speed. And so this works out really well for us. So with this, we get something called the Euler equations. And they look like this. As a note, I'm only writing one of them because there's two others for two different directions. I did bold here, but would change between the different versions. So that got rid of a bunch of our equations from earlier. You can see that part of that part of the material derivative did pop out here, the section that was not time dependent, but the rest of it got destroyed. So this is more useful. We can actually use this in a lot of problems. And there's a nice little shorthand for it too. We're going to take the dot product of the gradient multiplied by this guy right here. That is for the x direction once again. Okay, but can we simplify it more? We actually can. So let's do that. So another assumption we can make, which is less common in general aerodynamics, but will be very common for us, is that of incompressibility. And we already saw before that was when if it's incompressible, it means that the density is a constant. It doesn't change with time or position. And this is usually good if we have slow air, so less than 0.3 for a Mach number. It's technically not incompressible ever. It always compresses a little bit, but the air is really small as long as you're at low speeds. So my density is constant. That means it comes out of all those partial derivatives. It can just pop out because it's a constant. And that changes my equation a little bit more, because if I make one more assumption, which is that we're following a streamline, then we get the most famous equation in all of aerodynamics, which is Bernoulli's equations, which shows this. And all Bernoulli's is saying is that my pressure plus the dynamic pressure is equal to my pressure plus dynamic pressure at a second point. So this is point 1, this is point 2. If I were to have a wind tunnel, something like this, where it does, contract a little bit, I could use that knowledge to connect the 2 points, so long as I'm going along a streamline. And so I could figure out what P2 is if I knew V2 and P1 and V1, or any combination of. So long as I know 3 of them, I would know the 4th. Does it always work? So long as we're incompressible, it works really, really well. If we're not incompressible, it doesn't work at all. So that's it for this time. Thank you all for listening, and next time we're going to do an example using Bernoulli's equations. Have a good one. Bye-bye.